In our previous lesson, we were talking about the definite integral and also the area under the curve, whereby we said that the area between the curve, the x-axis, and also the lines that are passing through some point, x is equal to a and also x is equal to b, and we said that that is actually the area. So in a nutshell, let me just put this summary here so that at least we get a feel of what we were talking about last time. So we said that a definite integral is usually represented with an elongated s, whereby there is some value here, x is equal to a, and there is also another value there, x is equal to b, and of course you have a function here, f of x. Wait, this is not doing what thing. And then you have your dx there. We said that this is a definite integral. In other words, it is the area between the curve and the x-axis between these two points. And then from there, we said the definite integral is given by the limit as n approaches infinity of this sigma here, whereby you are having an I running from 1 up to n, and then we had f of x star, and then you have an I there, and then we will have your delta x there. And we said that this x star I, this one is actually the sample point. So it is a sample point, and this point is on the interval. On the interval. xi minus 1 and xi here. So this is a sample point. The second thing that we talked about, of course, this is just the limit, and this delta x here is actually the same as you take this b, you minus a, and then you divide by n. This is actually the length of each sub interval. And then we said that if, let's say, you start by talking about this b here, what is that b? And then we started to talk about b being the upper limit, as upper limit of integration. That's what we said. And then we said this a here is actually what we call the lower limit of integration. And then we said that if you start talking about this one here, this elongated s, this one is actually what we call the integral sign. That's what we said last time, excuse me. And then this f here, we actually said that this f, I'm trying to find a room here for this, so I'm going to put it somewhere there. So this f of x, we said it is an integrand. This is a d. It's an integrand. And then this one here does not have much of a meaning, except that we are saying that what we will focus on this function is just the independent variable that we'll be focusing on in this function is this x. That is what this thing means. And then when it comes to this whole thing, only this part, so when you look at that part, you have the sum from I equal to 1 up to n, f of x, and have that. This one is what we actually called Riemann sum. So it is the Riemann sum. Where am I putting this a here? So we have Riemann sum, and this Riemann sum is named after the German mathematician, which was usually called Bernard Riemann. He's one of the mathematicians who also contributed a lot when it comes to the integrals. That is why this sum is called Riemann sum, after the German mathematician Bernard Riemann. So that's what we said. This is just the notation whereby this is what we call the definite integral. Definite means that you must have a lower limit and the upper limit. That's what it means to have a definite integral. Now let's talk about this definite integral. So when you are having this definite integral from a to b of f of x dx, what is actually this definite integral? We said that this one is the net area. So it is a net area between the curve, f and between the curve f, the x-axis, and the x-axis, let me not put end here, the line the line x is equal to a, and the line x is equal to b. So it is the net, underline net, because it is not the total area, it is the net area. Let's take some example here. So suppose we're actually having a function. I'm gonna say this function, I'm gonna draw, let me put an EG here. So I am having this y-axis this side, and then I want to put the x-axis along this side, and then the y-axis, of course, I want to remove that, so we have an x. Suppose I have a nice function at this point here, I'm going to call it a, and then I have a nice function that is running all the way and then start coming up, and then it goes like this. And then this point here, I'm going to call this point, let me call this one b, this one c, or let me do it like this. This point is a, this one is b, and then this one is c, and this one is ad. What I want you to realize here also, now that I have that, I also wanted this function here, I want to call this function f of x. So this function is actually f of x. If, let's say, I want you to find the area, so I want you to find the area between the curve, this curve f, and the x-axis, and this line from a to b. So basically here, if let's say you are using the definite integral from a up to b of f of x dx, what is this going to be? So suppose this region here, I'm gonna call this region or this area here a1, and then this region here or this area that is there, I'm gonna call it a2, and then this one that is there, I'm gonna call it a3. So this area here is a3, and this area there, and this area there. Now if I wanted to find this definite integral, what am I actually looking for? What is actually going to happen here? We will notice that this area, because all the heights of the rectangles that I'm going to create here will have a positive height, so, and also the bases will be positive. So the area that I'm going to get here is going to be positive because the function is above the x-axis. But when it comes to this particular region here, you will find that f of x is negative, so all the area that we will end up getting here is going to be negative, and then this one here in this region we are actually end up having a positive area there. So if you wanted to find this definite integral. This definite integral is going to move. We're going to move from a up to c first, and then we have our f of x dx. And then we have to add the area of this particular region here, which is going to be from a up to, no, not a now, because we are starting from this position this way. Remember that this is the area now that we are focusing on, so we'll end up having a plus, and then of course you will end up having still f of x dx, but here we start at c and then we'll end at d. And then from there we start looking at this region here, so which starts at d, so you will end up having a d, and then we move all the way to b of f of x dx. So that is basically what is going to happen here. What I want you to notice about this definite integral is this area that is actually here, which is going to be the same as a1 and then plus. And then when you look into this area here, I want you to realize that actually here you are having a negative area, so you have a minus a2, and then this one is going to be positive, so we'll end up having a3. So basically you will have this area, and that area, because this one is negative, is going to reduce those two areas because it's negative. So what is that? This one is going to be the net area. So it is the net area under the curve. So this is the net area. So when you're moving from A to B, when you're having only that. But if you are looking for the total area, so the total, this is the net area because we have a negative area here and we just added without adding anything. So if let's say you want to find the total, you want to find the total area. So the total area, instead of having these things, you will have to take the integral from this position to that position, which is the same as just a, and then plus you want to find the absolute value of the second area, and then you want to also add the third area. I hope you can see the difference here, that you first have to move from this position to there. When you're arriving to this second portion, which is that, you just have to take the absolute value because the area is negative, and then when it comes to this one here, you have to end up realizing that it is also positive. Let me take an example here. I'm gonna take an example. So this example is going to say, number one, evaluate the definite integral from, I'm going to move from 0 up to let's say here 2 pi of sine of x dx. That is the first question. The second question, I want us to say, find the net area. So we want to find the net area be enclosed. Let me use enclosed, not between. The net area enclosed by the function. The net area enclosed by the function, I'm gonna say f of x is equal to sine of x. The x-axis, the x-axis, the line x is equal to 0, or I can say in this case x is equal to 0, the y-axis. Let me use y-axis so that you get used to it. The y-axis, and the line x is equal to 2 pi. So that is the second question. The third question is, find the total area enclosed by the function f of x is equal to sine of x, the x-axis, the y-axis, and the line x is equal to 2 pi. So that is what I want you to see. If you can see something here between 2 and 3, the only different words here, you just have a net, and here you have a total. This is very important when you are answering questions. In most cases, when the question is saying find the area enclosed, it means that whatever that area that you will end up dealing with, there is no need for you to distinguish between a net and a total, because it's going to be the same thing. Let's look now at the solution here. Let's start with the first one. Number 1 is saying we wanted to evaluate the definite integral from 0 up to 2 pi of sine of x dx. This one is very simple because it is just the definite integral. You don't have to draw anything, you just have to go through it and find out what you are actually getting. So if you look into this function here, the first thing that you need to realize here is this: what is the particular antiderivative of sine of x? Of course, if you are looking for the particular antiderivative of sine of x, you know that it is a minus cosine of x, which means that if I take the derivative of minus cosine of x, I will get sine of x. That is the meaning of that. And then I wanted to evaluate this when x is equal to 0 and when x is equal to a 2 pi. And then of course from there I know that what I will end up getting is minus cosine of 2 pi, and then from there I have to minus, but now I have a minus there, so I'll have a minus cosine of 0 inside. And then you know that this is going to be minus cosine of 2 pi, and then from there I have minus times a minus going to be positive, and then I have a cosine of 0. And then next, you know that this 2 pi is the same as 360 degrees. So whenever you are looking for a cosine, I know a cosine of 360 degrees, what is going to be that? That is a 1. So times a minus 1, I will end up having a minus 1, and then plus. What is cosine of 0? You know that cosine of 0 is the same as 1, so you have a 1. The answer that you are getting a 0 there. So this definite integral evaluates up to a 0. That is what is important there. The second equation here is saying to us find the net area enclosed by the function f of x is equal to sine of x plus x-axis and then y-axis. You know that y-axis is telling us that x is equal to 0 there, and then the line x is equal to that. So if you look into this, these are the x values, this one and that one. So this one is going to be the lower limit of integration, and this one is going to be the upper limit of integration. So the net area, so I'm going to write here, net area is equal to you put here the lower limit of integration, which was x is equal to 0, and then the upper limit, it was 2 pi, and then inside here we'll just put the function f of x, which is sine of x dx. And then let me try and draw this function so that you can see what I'm talking about here. This is not a good looking curve. So if let's say we were to draw sine of x, so I want us to draw something here so that you will see what I am talking about. So a sine function is at 0, it looks like this start going up, and then it go all the way, and then it comes down, and then it comes all the way, and then it comes up. And then I know that here we have 90 degrees or pi over 2, and then here we are having a pi, and then somewhere here we're having 270 degrees, and then you can add these two. You will have 3 pi over 2, and then here you will have a 2 pi. So we have a 2 pi there. This one is a function f of x is equal to sine of x, and this area here is the same as that area there, except this one is below the x-axis. So this one is negative and this one is positive. So when you're adding this area which is positive and you are adding to something that is negative but equal in magnitude, you'll find out that you're supposed to get a 0 net. That is why this one, because we found that we found it from here that this one here evaluates to 0, so the net area is going to be 0 here. So that is actually the net area, because this one, for starting from 0 up to pi, you are actually end up getting a positive area, but this one here is the same as that, except that it is below the x-axis and it is negative. And you can see here that we have one is negative, one is positive. That is why we are having those nice things there. Let's look at number 3 now. Number 3, we wanted to find the total area. So the total area. So if you wanted to find the total area, if let's say you had a paint and you wanted to paint this part and that part, you cannot say that you need to buy 0 paint. You need to buy a paint that's going to shade this region and a paint that is going to shade that region. So in order for us to be able to get the exact area of this and not end up cancelling out, I can say that we need to find the area from, so we need to have area from 0 to pi, and then plus the area from pi to 2 pi. So that is actually now going to be the total area. I hope you can see the difference between the net area. That the net area, you just have to find the definite integral. The answer you are getting is going to be the net, but when it comes to the total, you have to be careful that everything that you are getting is above the x-axis and you are getting a positive thing. So when it comes to this, you know that this is going to be integral from 0 to pi of sine of x dx, plus, because this one is negative, I want to take the absolute value of that area from pi, which is this pi, up to 2 pi of sine of x dx, because this one I know for sure is going to be a negative. That is what is important here, because I want to end up getting a positive thing. And if you look carefully on this part here, I know that I will end up getting what is the particular antiderivative of this. You know that the antiderivative of sine of x is going to be minus cosine of x. Of course, the derivative, I know that the derivative of sine is cos, but the derivative of minus cos is sine. And then this one needs to be evaluated when x is equal to 0 and when x is equal to a pi. And then plus the absolute value of the antiderivative of this is minus cosine of x. And then this one, I wanted to evaluate it when x is equal to pi and when x is equal to 2 pi. Of course, I'm looking for the absolute value of that. And then when it comes to this one, I will end up getting something like minus cosine of pi, and then minus cosine of a 0, and then of course this is the answer that I will get from here. And then come to this part here, I am looking for the absolute value here of whatever I'm gonna get inside. So I have a minus cosine of 2 pi, and then minus, because there is that minus, so I have to minus again a cosine of a pi. I have the absolute value there. The next thing here I wanted to make sure of is this. I have this, what is cosine of 180 degrees, was pi is 108. So I wanted to find minus cosine of 180 degrees. What is that? That is a 1. So I have this minus here, which is the same as that minus. So I want you to be aware that is 1. In other words, I know that cosine of 108 is actually in which quadrant? Second quadrant, and it's a cosine is not positive, so we have a negative 1 there. But in this particular case, because we already have a negative, so we have a 1. And then here, negative and a positive, I know that's just a positive. And then I have a cosine of 0. You know that cosine of 0, what am I doing now? Cosine of 0 is going to be a 1, so we have a 1 there. And then plus, I have an absolute value. What is cosine of 280? 360 degrees. Cosine of 360 degrees, we know for sure that it is a 1. So I'm going here to end up having a minus 1. Minus and a minus is a plus. Cosine of pi, I am looking for a cosine of pi, or simply put 180 degrees. That is supposed to be cosine of pi is going to be a minus 1. I hope you can see what is actually happening here, because we have this pi here which is actually minus we have this one here which is a minus 1, and then of course this and that is going to be positive, or simply put, I can do this. If we wanted to find this thing out, I can say that we wanted to find let me put this, where are these things here? Okay, let me just focus on the inside. I have a minus, I have a cosine, and then I have a 2 pi. 2 pi is the same as 180 times 2, which is the same as 360. And then from there I have minus, and then I am minusing cosine of 180 degrees. What is that? And you can see that is a minus 2 pi, which is the same as minus 2, which is that, but I have an absolute value. And then you can see that this plus that is a 2 plus. And then when it comes to this one here, I will end up having the absolute value minus 1 plus minus 1, that's minus 2. And then of course the absolute value of minus 2 is going to be a 2, and now you end up getting a 4. So this is the total area of this region plus the area of that region. We are actually end up having 4 units squared, because it is a total area. Bear in mind that when we're actually dealing with this one here, the net area, this one cancelled that is why we ended up having a 0 there, but the total area cannot be 0, it is actually a 4. Hope you can see the difference there, because those are one of the things that are important, the differentiation between the total area and the net area, and what is the definite integral. A definite integral, we know it by having upper limit, lower limit, and we know that whenever we wanted to evaluate the definite integral, whereby you have a there, b, and you are having f of x dx there, all you need to do, you need to find the particular antiderivative of this and evaluate it at b, and you subtract the particular antiderivative of that evaluated at A. That is what this thing is. As you can see here, this value here, we are trying to plug it there to get that, and this value, we are trying to plug it there to get that. That is the meaning of this thing here when you're evaluating that. And of course, this is the net area. As you can see here, it was a net area, but when it comes to the total area, you have to actually draw the curve to see if are you not actually having positive areas and negative areas, and they keep cancelling out, so that you can actually get the exact area for the total area. Now let's talk about this theorem here. You have a theorem. I hope you understood what I was talking about there. This theorem is saying if f is, we have this function f is continuous. It is continuous. So you have a continuous function on the interval ab. So we have this function is continuous. Or f, or if f has a finite. When we are saying finite, we are saying that you can count this thing and finish counting them. Has finite number of jump discontinuities. Finite number of jump discontinuities. Then f is integrable. F is integrable on the interval AB. It must be integrable. That is the definite integral. The definite integral AB f of x dx exists. So if you have a function and this function is continuous, then you know that if that is the case, then you will be able to find the definite integral. In other words, you find the particular antiderivative, and then you evaluate at that point, and you evaluate at that point, and then you find the difference. You are always going to get the answer. Or if f have a finite number of jump discontinuities, then it's guaranteed that you'll have a definite integral. Let's say, for instance, I'm just going to give you a quick example here. If, let's say, you have a function, and this function is like this, and here you have a hole, then up there is shaded, and then at this point this function is increasing like that. Because we only have this, you can see that I can draw this pen up here, and then when I want to continue I have to jump and start drawing there. You can see that we actually have to we only have this jump discontinuity. We are not talking about other discontinuities. We are only talking about this jump, a jump discontinuity. So when you are having this jump discontinuity, because the definite integral is just the area between the curve and the x-axis, then we can say that in this particular case the definite integral exists, or we can find the net area under the curve between that, as long as we can count the number of jump discontinuities, or f is just a smooth and continuous function on a given interval. I hope you can see what this theorem is actually talking about. That once I give you a finite number of jump discontinuities, you can always find the integral, or the definite integral. Now let's talk about the properties of definite. Let's first talk about the properties of the sigma notation what are the properties of sigma notation? So these are the things that you need to know. Of course, here we don't usually use them much because we're no longer using the understanding the old way of approaching integrals. We are using this this method instead of finding the creating these rectangles and stuff. We only use this most of the time because that one is tedious, but it's good for you to know that actually some of the properties that I'm going to give you for definite integrals, they actually come from these properties of sums, the properties of sums or sigma notation. So first, let C be a constant. If C be a constant, so we have C is a constant, then the first one is saying if I take the sum that is running from I equal to 1 up to n of a constant, the answer that I will get is the same as just taking n and multiplying it by a constant. The second one is if I want to find the sum that is running from I equal to 1 to n of C times some AI, this is a constant C, the answer that I'm going to get is the same as if I were to pull the constant out and take the sum from I equal to 1 to n of this AI, because that was a constant. The third one is saying if I want to find the sum that is running from I equal to 1 up to n of AI plus BI, the answer that I'm going to get is the same as if I were to take the sum running from 1 to n of AI first and also add it with the sum that is running from I equal to 1 to n of BI. In other words, I have these sequences, these two sequences. I can just split them into two and find the sum of the first n terms of this sequence and also find the sum of the first terms of this sequence. And for this one, you can see that this is a sequence, but there's a common factor. You can always pull out the common factor and find the sum of the new sequence of the first n terms. And then the fourth one is saying if you are having a sum running from I equal to 1 to n of AI minus BI, this is the same as just taking I equal to 1 to n and focus on one series and then subtract the sum of the second series, which is from n of BI. This is n, guys. So using these properties, we end up finding the properties of integrals. Properties of integrals. So we have these properties of definite integrals. We say that let C be a constant. So we have C is a constant. Then the first one here, we have the definite integral from a to b of a constant dx. If this is a constant, is a 5, is a root 2, is a 3, is a 2, 5. When you are evaluating this, you can just take the c and multiply b minus a. That's simple as that. So if you are having this, just take b minus a. That is what you need to do. It's one of the properties. And you have to know this so that you know how to evaluate definite integrals. And then if you here you are having a to b, and then you want to have a constant and it's multiplying a function times dx, you can always pull this constant out and just take the definite integral of f of x from a up to b and then multiply by that constant. So first take the definite integral of that and then multiply by a constant, because in most cases it is easy to find the definite integral of that function than with that constant, so we just want to pull the constant out. And then the third one is saying if you are having a definite integral from a to b of the addition of functions. You have f of x plus g of x, and then you have dx. Sometimes when you're having this, it's better for you to first find the definite integral of f of x alone from a to b, and then you add the definite integral of g of x from a to b. You have a dx. So sometimes it's easy to work with that than just dealing with this whole thing at the same time. And then the fourth one, of course, from a to b, if I have a difference of two functions, and then you have a plus, and then you have a g of x, and then you have a d of x. Of course, this one I don't want to have a plus, I have a minus. This one is always easy to first find the definite integral of the first function, and then have a minus, I have ab, and then I have g of x dx. So you can deal with that. When it comes to the product of two functions, that's actually a different case. Because if you have a product of two functions and you don't know direct their particular antiderivative, there is one method to do that, but is not within the scope of this course. And also the division means that you are actually end up having functions that are being divided together. One way to do that is actually doing the opposite of the chain rule, which is a substitution rule. And sometimes if the substitution rule cannot work, you have to do one of the methods which is beyond the scope of this course, is integration by parts. So it's not within this course. So for us, I want us to look at these basic properties. I want you to know that. And then we also have three more. I usually separate them and say comparison properties of the integral. Some instructors prefer to combine them as one thing. It doesn't mean that it's wrong or right. For me, I like to separate them for one good reason, because they are comparing two things. Of course, here we still okay, let me just leave it like that. I prefer to just separate them because they are way too different than those that are above. So we have this 5 there. Supposed to start at 5. So if let's say you have a function f of x, and this function is always positive or equal to 0 for all x that are between a and b, then when I'm taking the definite integral from a to b of this function f of x, because this function is always bigger than or equal to 0, then the net area must always be bigger or equal to 0. That is actually a common sense, because this is saying the function is always above the x-axis. So if let's say you have something like this, so the function is always above the x-axis or 0, so it's going like that. You can see that we will have a positive area there, whether we like it or not. That is what this one is saying. The sixth one is saying, if I have two functions, but this function is actually bigger than g of x, for all x that is running between b and a, then whenever I am taking the definite integral from a to b of f of x, it must be bigger than the definite integral from a to b of g of x dx. What I also want you to do, because it is kind of straightforward. There is no big deal about this, because this function is always bigger, then it has to produce a bigger net area. That is what is important there. The last one, I would say that if I have some number m. So I have this number m, and this number m is less than this function f of x, and this function is less than the capital letter M for all values x that are between a and b. Then the definite integral from a to b of m with respect to x must be less than or equal to the definite integral of a to b of f of x dx, and this must be less than or equal to the definite integral from a to b of m dx. What is important here, I want you to also realize that some textbook, because this is a constant and that is a constant, and you know that the definite integral of a constant, you just take the constant multiplied by the difference between these two, like that. Some textbooks usually just say that m times b minus a must be less than or equal to the definite integral from a to b of f of x dx, and this one is less than or equal to capital letter M times b minus a. Yeah, so some of us who might end up taking, I think, measure theory, they will end up using this a lot when they are proving things, but this one is also one of the important properties. I hope you have copied all these nice properties and all these ones here, properties of sigma notation, or just Roman sums are usually, no, do not say Roman sums, just sums, because I know that Roman sums have to do with f of x star. So that is what is important there. Then we also have evaluation theorem. We have been using this theorem, but now I have to state it here. So evaluation theorem is saying if a function f is continuous, it is continuous on the interval. So it is continuous on this interval. Let me call the interval AB. Then when I wanted to evaluate the definite integral from a to b of f of x dx, all I need to do, I need to find the particular antiderivative of this and then evaluate at b. So this must be equal to f of b minus capital letter F of a, whereby f of x is a particular antiderivative of that. Let me just write here, where capital letter F of x is any antiderivative of f. That is, if I take the derivative of this with respect to x, I get f of x. That's what we mean. We have been using this a lot when we're finding the net area, because I was trying, when we're doing antiderivatives and the area under the curve, I was actually trying to make sure that we end up seeing why these things are actually the same. So they are the same because of the evaluation theorem. When someone is asking you evaluation theorem, you must know that they want this statement there. Let me see if I have some examples now so that we can work on these examples. And then, of course, after working with these examples, I want us to end up talking about what I call the fundamental theorem of calculus. So let me look at examples here. Examples. So what are the examples? Evaluate or let me not say evaluate here. but most cases when they want you to find this, they usually say evaluate. Let me say find or calculate the value of the integral or definite integral from 1 up to 2 of f of x dx, where number 1 I have f of x is equal to x cubed, and then number 2 I have f of x is equal to x squared plus 1 over square root x, and then the third one we are having f of x is equal to 2e of x and then minus pi times sine of x. So let's look into this. What is the solution? So number 1, we wanted to end up finding the definite integral from 1 up to 2 of x cubed dx. What is the particular antiderivative of this? I usually put something like this, square brackets, and then find the particular antiderivative of this. The particular antiderivative of a power function is always going to be x. I keep the exponent, I add a 1, and then I divide by 3 plus 1, and then of course I place the x equal to 1 here and x is equal to 2 there, and then the next thing is going to be, I still have this, and then here I will have x raised to a 4 divided by a 4, and then I have x is equal to 2, and then I have x is equal to a 1. The next thing that I want to do, I want to evaluate here, so I'll have a 2 raised to 4 over 4, and then minus, and then I have a 1 raised to 4 divided by a 4, and then the final answer is going to be 2 times 2 times 2 times 2. This one is 4, this one is 4, this one is 4. 4 times 4 is 16, so we have 16 over a 4, and then we have minus 1 over a 4, and then the final answer is going to be 16 minus 1 all over a 4, which is the same as 15 over a 4. That is the final answer. And then let's go and look at number 2. What is number 2? We want to find the definite integral from 1 to 2 of x squared plus 1 over square root of x. We have a dx there. Just double check if this is what I wrote. X squared plus that. And the next thing that I want you to realize here is that this is the same thing as having a 2, and then I have an x squared plus 1 over x raised to 1 over 2 dx. And I also want you to realize this is the same thing as, I still have an x squared plus, and then for this one we have an x raised to minus 1 over 2, and then I have a dx. The next thing is, I wanted to find, because I have an addition of two functions, I can find the definite integral of the first and the definite integral of the second, which is not a big deal. Let me just find these definite integrals. But now what I'm going to do, I'm going to have brackets here, and then here, what is the antiderivative of that? We are going to end up having x, I have a 2, you add a 1, and then you divide by 2 plus a 1. Take note that we are looking for the particular antiderivative when we have the lower limit and the upper limit. And then here also you have minus 1 over 2, you add a 1, and then you divide by negative 1 over 2, you add a 1, and then of course want to evaluate when x is equal to 1 and when x is equal to 2. The next thing that I want us to do here is, let's first simplify. This one is x raised to 3 over a 3, and then plus, and then I have x raised to 1 over 2, because 1 is the same as 2 over 2, same as 2 over 2. So 2 minus 1 is 1, and then the common denominator is a 2. And then in the denominator, still going to have 1 over a 2. And then I want to evaluate when x is equal to 1 and when x is equal to 2. And then from there, you can move faster and say that, okay, now we are having x raised to 3 divided by 3, and then you have a plus, and then here I can change this division here, which is the biggest, into multiplication. If I change that, the denominator becomes a numerator and the numerator becomes a denominator. So this is going to be 2 times x raised to 1 over 2, and then you end up having x is equal to 1, and then you have x is equal to a 2. And if you proceed here, you will find out that you have x raised to 3 over 3, and then plus 2 root x, and then you have x is equal to 1, and you have x is equal to 2, and then we can start evaluating. So the first part we'll just plug in 2, so we'll have 2 raised to 3 divided by 3 plus 2 square root 2, and then minus, I'm going to open brackets, and then I'm going to have 1 cube divided by 3 plus 2 times square root 1, and then I close my brackets. The next thing is going to be, what is that going to be? This is going to be 8 over 3 plus 2 root 2 minus 1 over 3 minus 2, because root 1 is just a 1. And then of course I can just try and simplify this and make it look good. 8, because I have a 3, so I'm going to say 8 minus 1 is going to be 7 over a 3 plus this one and that one. I have a 2, which is a common factor, and then if I take the 2 out, I will actually be left with root 2. If I take the 2 out, I will have a minus 1 there. That's how simple this thing is. And then you can end it there. Okay, you can approximate it. I don't give a damn. The third one is, where's the third one? The third one was saying, I wanted us to find the definite integral of this, but the lower limit is 1, the upper limit is a 2. So, number 3, we are saying that we want to say evaluate 1 to 2 of 2e. We have 2e to the power x, open brackets, and then you have minus pi sine of x dx. Let me go up a little bit just to double check. So we're having this pi sine of x, of course, and then we have a dx. Simply put, this is going to be the same from 1 up to 2. I'm going to split this into 2 functions, so it's going to be 2 times e dx minus, and then I'm going to have 1 up to 2 of pi sine of x dx. The next thing that I want us to do, because this is a constant, I want to pull it out of the integral. So I'll have a 2, and then I'll have a 1 raised to, moving from 1 up to 2, and then I'll have e raised to x dx minus from 1 to 2. I'm pulling this because this is a constant. It's going to be in front of the integral sign, and then I have a sine of x dx. The next thing that I want us to do now is, what is, I still have a 2 there. Now I want to deal with this thing. What is the antiderivative of this? You know that the antiderivative of e to the power x is the same as e to the power x, and then evaluated when x is equal to 1 and when x is equal to 2, and then minus, I have a pi. What is the antiderivative of sine of x? We know that it is minus cosine of x, and this one is going to be evaluated when x is equal to 1 and when x is equal to a 2. The next thing that I want us to actually do here is, I want us to actually end up dealing with this. I still have a 2, open brackets. I take this value, I plug it inside, I end up having e raised to 2 minus e raised to, I take this and plug it there, e raised to 1 minus pi, and then inside here, I can just say I am going to multiply this minus and that minus to end up having a plus here, and then end up having a cosine of x, and then evaluated when x is equal to 1 and when x is equal to a 2. The next thing is going to be a 2, and then I still have e squared minus e1, and then I have a plus, and then here I will end up having cosine of 2 minus cosine of 1, right? And then of course, now that I'm having this, I think this is just the final thing, because there is nothing that can be done here to move further. This is the final answer, so you can stop here unless you want to approximate it with a calculator. So let us end here, and in the next lesson we'll talk about what I call the fundamental theorem of calculus. So let us end at this point here.